Hi, I'm Josh.
And I'm Jackson.
This is Enigma Explained. So in our last video, hopefully you saw we went through our example up here. Now we are going to talk about what actually happens when these rotors turn, what is the effect of that on the permutation, and also what is a permutation. So let's just see here. So we have this picture, and this is essentially a wheel in its A setting. And what I want to highlight here is in the A setting, every letter comes in like at a position here from, let's say, the right side, hits a contact here. So A goes straight to A. And in our current permutation, we see A is mapped to E, which leaves as E. So in the A setting on our machine, a signal arriving from a C position goes into the C contact, which we see here. So A position goes in on the A contact, B goes to B, and so on. Now when it leaves the wheel, so on this bottom side here, a signal leaving from a C contact exits at the C position. So we see if something is translated to the C contact, it leaves in the C position, same for B, same for A, and all the other letters here. So now let's see what happens when the wheel is rotated by 1 to the B setting. So down here, we see the positions on the outside are the same, right? So we have A through Z here, we have A through Z here. Same on the, let's say, left side, we have A through Z, and again, A through Z. So the positions all match up. The difference is which contact these positions are mapped to. So here we had A maps to A, now we have A maps to B in the B setting. So we see that when the wheel is rotated by 1 to the B setting, a signal arriving at the C position goes into D on the contact. So here the C position actually goes into D. Same for B goes to C. So everything kind of goes up 1 because we are in essentially position kind of 1. We've gone up 1 position. Sorry, we've gone up 1 setting. So if we kind of move everything to numbers, so A is 0, so we're starting from 0, we can say when the wheel is in setting K, it's K setting, and a signal enters at position P, so let's say we're in setting 1, so the B setting, and we enter position P, so let's say A, the position enters the P plus K mod 26 contact on the wheel. So what is P here? Well, we said in our little example, we're starting at A, so P is 0. We said it's K setting, so in our B setting, that K is 1. So P plus K is just 1 mod 26. And mod 26 is just making sure our numbers are in the range 0 to 25, which is the length of our alphabet here. So position P, we said P was A, so 0. Setting K, K is 1, so the 1 contact, so A enters as B. So now on the other side, a signal exiting through the C contact does so at the C minus K position. So note the difference. When we're coming in, we add the setting. When we're going out, we subtracted the setting. So here, we say something exiting at the C contact, so C is 2. We're going to subtract the setting, which is 1, and actually exit at the B position. So C minus 1 mod 26 gets us B. Yeah, so if any of this is unclear, be sure to kind of ask in the comments. Essentially, when we have these rotors at different settings, it affects the permutation. And when we're coming in, we were adding the setting to the position, and going out, we subtract the setting from the contact. So now we're going to talk about these permutations and kind of what they are. How do we represent them? Down here. So first we're going to kind of decide on a way to represent permutations. And the way we decided was cycle representation. So any permutation is just a bunch of cycles. And if we see something like this just means A maps to E. So in the forward direction, A maps to E. E maps to L maps to T, and so on, all the way to the end, which wraps back around. That's our cycle. So now U maps back to A. And we see this for all of our cycles. And one important one to note is that S is all by itself, which just means S maps to itself. So S kind of wraps around back to itself. So now if we go in the reverse direction, instead of going kind of left to right, we're going to go right to left. So we see U will map to R, which is to its left. This is in the inverse permutation. And we're going to go U to R, so on and so on, all the way back to A, which will now wrap around to U. And still, we see that cycles or permutations, where it's just S mapping to itself, is the same in the forward and reverse direction. One thing to note is that each letter should appear in only one cycle, so it's ambiguous. So in this particular permutation, A only maps to E in the forward direction. There is no A in any other cycles here. So since we said S maps to itself and we chose to kind of show that, we will also say that if a letter is left out of any of these cycles here, so if the S actually never appeared, you could then assume that S mapped to itself. So if a letter is left out of all cycles, it simply maps to itself. And these are the these were the standard permutations for each of the rotors used in the German Navy Enigma machines. So these were preset. You will see later on that actually we're going to kind of provide the permutation for each rotor as a configuration when we actually run our Enigma machine. Yeah, so we're going to stop that here, and later on we're going to go through this example here. But by now you should be comfortable with how the rotors rotate. We talked about double stepping. We talked about when a rotor rotates, what does that mean for its permutation. We talked about the actual permutation representation down here and how each letter maps to another letter. And now we're going to go through a bit of a longer example in the next video. So see you then.